Okay, I'm Yipeng and Sameh there. If you have questions about this talk, you can talk to me or Sameh offline. He's a very smart person. Okay, so legal notice. This is a collaborative work with my team member Charlie and Ren, and also Antonio contribute a lot to this work. So OvS is a pretty popular virtual switch in data center and NFV environments. We all know that. And that's why it's very important to improve the speed of OvS, the data path. So before we goes into any details about our proposal, first a brief introduction or refresh of the mechanism of current OvS flow lookup path. So basically, OvS has three layers of cache to do the packet classification. The first layer called exact match cache. So exact match cache means like your packet come, it's just basically a big hash table. So you look up in the hash table to find the header of the packet, and if you find the match, then you return the rules or the actions. The second layer called megaflow cache, which means if your packet misses the exact match cache, you will go to the megaflow cache. Megaflow cache basically composes of a series of subtables or hash tables. Each one has a mask. Mask means like each table will have different wildcard fields. So each packet header will be masked by the mask and then look into the hash table. So you can see this is a sequential search process to go through all the subtables or tuples. It's also a tuple space search algorithm if you are familiar with classification algorithms. The final layer called OpenFlow layer is also a tuple space search algorithm, but the major difference between the OpenFlow layer and the megaflow cache is that the megaflow cache will not have overlapping rules, which means like once you find a match in one of the tables, you can return immediately because there will not be overlapping rules. You don't have to like search all the tables, get all the rules, and compare the priorities of all of the rules and get the highest priority one. That's why we need this megaflow layer, because it enormously speed up the lookup process, because you can return as soon as possible. So this is a brief introduction. I guess Ben's paper has a more detailed and better description of this mechanism, but I hope this gives you a big picture of how it works. You can see, so this mechanism actually, I believe, is very good. It strikes a very good balance between the lookup speed, memory efficiency, update speed. If you read the code, you can find people put a lot of efforts. A lot of you put a lot of efforts on the algorithm and the mechanism. The design is pretty good. But you can see there's one problem very obviously, that it's not very scalable with regarding to the subtable count, which means like you need to do the sequential search. If you have a large number of subtables, your cycles is the cycle times the number of tuples, right? That's what we focus on for our proposal. So we do some little test with our synthetic traffic. We found like the megaflow search could take a very significant portion of the total execution time. That's some VTunes data we collect. So before, beside of the OvS, so my colleague Sameh yesterday presented the membership library in the DPDK conference. So I will briefly discuss what is a membership test. So membership test means like if you have a key or a header of a packet, you want to quickly find if this key or header belongs to a set of keys or not. So for example, here on this slide, I have a set of flows that you want to blacklist or you want to block. So the client sends some packets. You want to quickly find if the key of the packet belongs to the set or not. So definitely, of course, you can use a full-blown list array hash table to do this task. But that will be very memory inefficient and pretty slow. That's why we need a new membership test structure. We call it membership library. So by using this membership structure, you can have much faster lookup speed, which means like you can immediately know if this K belongs to this set or not. So I will cover more details in the subsequent slides. But this is just a new library. It will come with the DPDK 1711, and please try it out. So this is a more detailed example. Your KXCOM, the set summary is the membership structure. It will immediately return you a result. Yes or no means like, yes means like you belong to this set, and it also returns a target number. If you belong to that set, what target you want to go to, right? And if no, then we will immediately return a 0 to you. So that's a basic feature of membership library. So how do we use this membership structure to speed up OVS Megaflow search? Actually, the idea is pretty intuitive. That before package goes to the Megaflow cache, we will have another layer of indirect table realized by this membership structure. We call it Cuckoo distributor because we started this project with the Cuckoo hash table concept, and later on evolved to membership and everything. So the process is like this. So your packet comes first, go through the EMC cache. If it misses the EMC cache, it then will go to the Cuckoo distributor. Not directly go to your subtable, do the sequential search, but it goes to go through the Cuckoo distributor. The Cuckoo distributor will immediately give you the index of the tuple you want to go to. So you don't need to do the sequential search. Basically, you now only need to do one distributor lookup and one subtable lookup. So people always ask me, why do you need this another layer of cache? Why don't just use a memory for EMC or whatever, right? That's a major, that's actually the fundamental difference between a hash table and a membership structure. A hash table, you need to store the full key. So for EMC, you probably need like 500 bytes for each entry. Obviously, not every byte you will need to bring to the hardware cache, but still one entry will occupy one hardware cache. So pretty quickly, you will blow out your L1 cache and L2 cache. So, but for Cuckoo distributor, we use 4 bytes for each entry, which means a 4 megabytes structure can contain 1 million flows. So if your traffic pattern has 1 million flows or less, it will be perfectly stay in the Cuckoo distributor and speed up your Megaflow cache search. So our mechanism is orthogonal, a complement to the tuple ranking, subtable ranking mechanism in the OVS. So yeah, let me describe a little bit about tuple ranking. Tuple ranking means like it will always rank the most hated subtable at the front. So your packet will search that tuple at first. That will increase your probability to find the match at the first subtable, right? That works very well and very effective, but can't deal with the case that if your traffic pattern has a uniform distribution, which means like all the packet will go to random tuples with the uniform distribution. That's where Cuckoo distributor could help. So both two mechanisms complement each other. They are orthogonal mechanisms. So we propose another mechanism called dynamic turn on or turn off, which means like if your tuples ranking algorithm works so well, or you only have one tuple, we don't want the Cuckoo distributor harm your performance, right? So because this is another layer of cache, you may not always want it. So if your tuple ranking mechanism works so well, the Cuckoo distributor will turn it off automatically. so that when it's needed, it will turn it on by itself. When it's not needed, it will just turn it off by itself. This is the font probably too small, but this is just a simple flow chart of the mechanism. The green box is the current flow in the OVS, and we add our membership library API calls in between. Basically, just to check the indirect table first, and if I found a hit, I just directly go to that tuple. If I find a miss, I just do the original sequential search. Yeah. So this is some old data, but you can find the new one on the mailing list. We post a patch, new patch recently. After DPDK 17.11 come out, we will have a new patch depending on the membership library. Sorry. So this is some old data, but it basically we can have a 2 to 3x improvement. This is some synthetic traffic pattern. We are not saying like our mechanism works this well for every traffic pattern. For example, if your traffic only have one tuple, then obviously Kuku distributor will not help. But in certain cases, if you have many tuples, many subtables, Kuku distributor probably will help you. Actually, we tried the class bench. If you know that, it's a synthetic benchmark. It has like hundreds of tables or subtables. I'm not saying they are realistic, but in such kind of cases, you probably want a Kuku distributor to help. In that case, the Kuku distributor help about 3 to 4x speed up in that case. Oh, sorry. OK. So as a conclusion, Megaflow lookup has some scalability issue, especially with the uniform distributed traffic pattern. We use membership library to optimize this path and achieve like 2 to 3x in certain cases. Basically, it's the idea to add another layer of indirect table between the Megaflow cache and the EMC cache. It is super memory efficient, very fast, not like some big hash table that you can contain like 1 million flows within 4 megabytes space. It has a dynamic turn on, turn off mechanism so that it will probably not harm your performance in cases that you don't need Kuku distributor. And since DPDK comes out yesterday, we will prepare for the new patch with the DPDK dependency. So with the DPDK membership library dependency, the OVS code size is pretty small. We only have to add tens of lines of code to realize this. It's pretty simple concepts and won't make the data path furthermore complex. OK, that's it. Thank you, everyone. Any questions?
So before we go to audience questions, I have the privilege of being able to ask my own question. So you talked quite a bit about how it's used in the effects and so on. How does it work internally? Maybe this was covered yesterday, but I missed the talk.
You mean the membership library?
Right.
So if you are familiar with blown filter, the fundamental concept is similar as a blown filter. We call it a membership test structure, but actually it's a filter type of structure. So we have two different structures to realize this filter feature. One is a hash table based. The other is a blown filter based. So for hash table based, it's basically a Kuku hash table without the case, which means the full case storing in the hash table. We have a small size of signature. We use that signature to decide if your K belongs to this set or not. So you can see, yeah, I forgot to mention, like you can see there's some possibility you will have a false positive, just like the blown filter. So this is not a 100% accurate table, like the hash table, but still it can do the work because 99% of the time you will find the correct tuples, the subtables to go to. The 99.9% of your packet will be speed up, and the left will be fallback to the original OVS megaflow search. So generally, it gives you like 2 to 3x.
Great. So if we have any questions from the audience, I don't see mics set up, but
You talked about the signature that you use for the membership test. How do you derive this signature for looking up a packet?
So in the patch, we use the RSS signature. Just the hash calculated for the EMC, we just use that. So it won't incur any hashing overhead, additional hashing overhead.
So question about the cuckoo distributor. So traditionally, cuckoo hashing, when update, you might hit the problem of conflict, and then you have to propagate the
Cuckoo
conflict
path.
entry. Yeah. So do you have similar problem in this case?
Yeah, so we start with that cuckoo hashing mechanism. Cuckoo, to who you may not familiar with cuckoo hash, is that for a hash table, you want the load factor to be as high as possible. So cuckoo hash means like when you insert a key, you find a collision, you move the existing key to another entry. That's what you mean, right? So in this, in our OVS mechanism, we don't need that because it acts as a cache, which means like we don't need to care about the load factor that much. Because it's a cache, so it refreshes its own content automatically. So new keys will replace the old keys automatically. So if we implement a cuckoo hash exactly like within the cuckoo path and stuff, when the table is full, the speed will drop significantly. So we start with that, but actually we don't use a cuckoo path. Eventually we remove that. That's a good question. So the name cuckoo actually not there anymore. So
Thank you.
Thank you.
Hi. So Bloom filter uses several hash functions. So what you said is you use the RSS value as a hash value, but how do you compute other hash values? And do you need to touch the packet fields like several times?
Yeah, actually, if we use Bloom filter, we would definitely need like couple of hash functions on the header, right? That would be too much maybe. So we use actually a hash table based structure, which means we use two hash function actually to get two locations in this hash table and compare that signature. So, and this signature we derived from the RSS hash used by the EMC, so it doesn't incur any more additional hashing overhead. So, but you are right, like if we use a Bloom filter, that probably need more overhead. That's why we choose to use a hash table based from the membership library. Thank you.
We have time for another question if anybody has one.
There.
Thank you, Yipen. I know if you use a blue filter, you need to save key or hash table in cache, right?
We actually didn't use a Bloom filter. We use a hash table-based filter. So they both serve as a filter feature, but we have different implementations in the membership library. A Bloom filter is a structure that you need to calculate multiple hashes. And in a big bit array, you need to check those bits in a big bitmap. But in this structure, we use a hash table-based filter, which means we have a hash table, and we check the key into the hash table, and we compare a short signature. So they both are filters, but actually we didn't use Bloom filter. Yeah, so yeah, I know that filters is complex, but we can discuss offline.
All right, let's thank our speaker.
Thank you.